Well, looks like we're at start time, so I'll go ahead and get us started. Welcome back. Probably don't need to remind you, the last time we were together on Tuesday, you took an exam. Pretty long exam, a pretty hard exam. Hope it went well for you and you didn't think it was hard. Probably not the case, but obviously, or maybe it's not obvious, I don't have them to pass back yet. I'll need the weekend to do all 100 plus of you and all those ones there. So that'll be what I will do probably starting tomorrow, and then, anyways, hopefully everything will go right, and I'll give it back to you on Tuesday. That's normally what I do. I've also not ever had this many students, but I think I can still finish it up over the weekend and give it back on Tuesday. So that's the game plan. Meanwhile, we'll go on to the next section here, chapter 27. You question? Oh, no, I didn't bring the capacitor. Okay. Remind me when we're in lab so I can get it out and get it ready and get it all to go. Yeah, I forgot. No, I forgot all about the capacitor again. All right, so one of these times before the semester's over, we'll remember. This way the anticipation is just building. Then it probably won't work. It'll be a fool. All right. But anyways, with that said, test given back to you on Tuesday. We got started a little bit on the next chapter, if you remember, a week ago. We had, towards the end of class, I think a little more than a half hour, if I remember right on the time, that we said, okay, let's start looking at chapter 27. And so here's my hope, to do most of 27, maybe even all of 27. I think there'll be plenty of time to finish talking about 27 and then even do a couple of examples. And then I'll have to debate on Tuesday if we should do more examples from 27. And I'm kind of thinking maybe we probably should. But I think you'll discover, if you haven't already, that 27 is probably the simplest of the chapters we've done so far. Right? We had three really tough ones at the beginning. Then the capacitor one, which was a little easier, I think. And now this one's even easier too. And it really just has a main theme. And the main theme here is really to get you to understand about current and resistance. And so that's where I want to start again. You might remember that we spent most of our time talking about the idea of current. And I'll review this real quick and then go back to resistance where we left off. But it is that the point of this chapter is to get you to understand what is current and what is resistance. Next chapter, we will take that a step further and start hooking those into circuits and understanding our circuits much better. We'll do a little bit of circuits too before this chapter is done. But really the main point is the fundamental idea: what is current? What creates the current? What is resistance? What creates that resistance? And that's really what we're going to focus on. So I'll start here with current. What is current? And so maybe this is a good way to define current. It is moving electrical charges. This is that figure 1. You saw this on Thursday when we did this. I said, look, imagine a wire. And this little yellowish cross-section is supposed to be a cross-section of a wire. And if some charges flow through there, then that is the current. And so current is moving charges. And so we started with this little diagram. In fact, we went one step further. We said, how shall we define current? And we said current was essentially the rate at which charge is flowing. Okay? Now, the reason that's important is because I don't want you to think that current is the number of particles that are flowing. I also don't want you to think that current is in the same direction that the particles are flowing. You remember that discussion? That is not the definition of current. Yet sometimes we get that, I think, concept in our mind. The definition of current is the amount of charge that is flowing. So how much charge flows would depend not only on how many particles are flowing, but how much charge does each particle have. And the direction would depend whether or not the charges are positive or negative. In other words, this little arrowhead down here and this little picture here, I think is the simplest cases we could say. We would say that the current flows, and that's what this purple line is for, the current is flowing that way, because the flow of charge is that way. When a positive goes from here through there, there is a charge change that goes from here to here, and that's what current is. Now I say all that to remind you then of the second picture that we saw, is we left that picture and went to a more realistic case of what could happen in where we have both positive and negative, or just all negatives, or just all positive. And so if we look at B, B is that one that I think is the simplest. It is saying, look, the positive charges are going that way. So what is the direction of the current? Well, if the positives are going that way, then that is the direction of the current. But yet on the other hand, if I come over here and I say, look at these negatives, and the negatives are going this way, what direction is the flow of charge? That way, right? And so that was an important part I wanted to make sure you saw, and thought I would start today by reviewing that say, look, this is what we are after in this chapter, this mental picture of what is current. Current is flowing charges. Okay? Now, granted, those charges are connected to particles, but it is not necessarily the direction of the current is the direction of the flow of the particles, because there's a difference between a positive and a negative. And in more realistic pictures like this, where you have things like a liquid, when you have these ions, you got both flowing. And of course, as we learned before, that to make these flow, you would be putting a force on them. That force would come from an electric field. And this one shows positives going that way. So the electric field must be this way because it's pushing positives, which also means negatives flow that way. And so you have some particles, in this case, going to the right, the positives, and you have negatives going to the left. But which way is the current? Do those cancel out? No, they don't cancel out, right? A positive going this way is the same as a negative going that way in terms of the flow of charge. So the current is this way. It's as if all five were positive going that way. Or it's as if all five were negative going that way. Okay? But what I really have is three positives going to the right and two negatives going to the left. But all five of those contribute to the current. It's not like they cancel. You go 5 minus 2. No. It is, I'm sorry, did I say how? Yeah. It's not like it's 3 minus 2. It is 3 plus 2. Get my point? And so I want to emphasize, again, what is current? Well, the current is the flow of charges. Okay, fair enough. But it's defined as how the charge flows, not the particles. All right? And so, like I said, current then would be in the same direction as a moving positive. But current would be opposite to the direction of a negative. Now, I guess this is kind of the same argument, so I won't go there. But we've already learned that in wires and things, the stuff that's moving around really are the negatives. And so you're going to see here that when we have a lot of our discussions, we're going to talk about the direction of the current, and that's going to be opposite of the direction that the negatives move. Okay? Now that doesn't happen in all things. As I said, silicon or doped silicon would be a good example here of where the positives, all positives were flowing. Or some kind of liquid in a battery would have both ions. There's another good example. So again, hopefully not spending too much time here, just want to make sure you have that concept. What is current? Current is these moving of charges. And in fact then, what are the units used to measure current? Yeah, and so if you see it here, you could say it is a coulomb per second, right? And if these are little electrons, of course you can tie it back to what I would call a microscopic view, because 6 billion electrons is 1 coulomb of charge. And so if I have my little metal wire and the negative electrons are moving, this only shows 2, but if we put 6 billion here and they flowed that way in 1 second, then I would say the current is this way, and it is 1 coulomb every second, which many of you already said. It's called an amp. And we give it a symbol A for an amp. So we will be measuring our current in amps. Well, one more thing in this quick review, since we did it a week ago and I suspected you were probably well focused on the test, not so much this, that if I put a picture like this on here, okay, here is again supposed to be this microscopic view of what is happening inside of this wire. And if I go ahead and maybe I'll draw this picture a little bit more. So they say, okay, let's take this battery. So here's my battery. I'll just say it's 12 volts. And so here's this wire. And then I'll just kind of circle the wire around here. But maybe this is the part in the picture that we're focusing on here. Okay? The electrons would be going this way. Actually, to make it, which way are the electrons going in that one? Okay, I tell you what, to make it match the picture up there, I'll put the positive side of the battery here. So the electrons would then be moving in this direction, which is the direction of our picture. The electric field then, of course, would be pointing in the opposite direction. And so there's the electric field that then is pushing on the electrons. And again, notice the electrons move opposite to the direction of the electric field. That's not a surprise. That was our earlier material that we learned, right? The electric field is the direction that positives would move, and these are negatives. But again, just want to remind you that when you think of these in your head and these electrons on a microscopic level, please remember that they are moving in what you might define as two different speeds. The first speed is actually how fast are they moving. If you actually measured how quickly does it go from here to here, you know, you would get something in the neighborhood of 1,000,000 meters per second. It's really, really fast. And yet, they don't necessarily drift down the wire very fast. Because what's happening is they ricochet around. And they don't really show any backwards motion. Oh, well, here's a little backwards motion. But as they bounce off of each other and as the atoms in this piece of metal, their 1,000,000 meters per second really results in less than a centimeter per second drifting down the wire. And so we want to be careful as we talk about those two speeds, because we left off with this calculation. We said the current then in that wire was an N, an A drift velocity, and the charge. And that's what I am mentioning here, that this drift speed can be pretty small. I mean, we're talking about a millimeter per second. So they don't drift down the wire that quickly. That's the point I'm trying to say. Individually, they're moving very fast, but they're ricocheting around. And I don't think this picture does it justice. It'll do a lot more of this. And there's a lot of backwards motion by the time it barely drifts. So it does have a speed down the wire, that drift speed, really, really small is my point. Now, fortunately, these electrons are really, really small, and so when I take a wire and they drift down there, even though they only move a millimeter in 1 second, that's a lot of electrons. In 1 second. If you take how many electrons are in a piece of copper that is 1 millimeter in length, that could be quite a bit of current. So even though they only go at a slow speed, this can be a lot of electrons and even a lot of current. Because we need 6 billion just to get 1 amp. But this could be 2, 3, 4 amps. You know, if it's 4 amps, that's 4 times 6 billion. That's how many electrons would be compacted into that 1 millimeter of space there. So like I said, I want to just kind of begin our discussion back with a quick review of what current is. Because then I want to address step 2, which is what we called resistance. And that's where we left off here. We got talking a little bit about it. I showed you kind of a few of these simple demos I have to try to give you a mental picture of what's going on. But now let's try to do this in a little bit more detail and say, okay, what is resistance? Why is there a resistance? What do you mean by that word resistance here? And maybe I'll just start by saying this is a way of measuring what is stopping these electrons or ions, you know, whatever the charges are, from moving. They don't, I should always emphasize that, they don't have to be electrons. They usually are, so it's a good place to start here, but anything that is flowing. And I like the way your book does it. Your book starts off by saying this. He says often, not always, but often, this happens. That is, if you apply an electric field to some kind of wire. And this picture kind of illustrates it. If you apply an electric field, wouldn't that make these charges start to move? What do you think might happen if you doubled that electric field? Yeah, faster. And oftentimes they move twice as fast. What would that say back here? What would that do to your current? It would be twice as much. Now, that doesn't always happen that way, but a lot of times it does. And this was discovered by a guy named Ohm. And so Ohm's logic, and what we're going to call Ohm's law here in a moment, is something along this way. Your author starts off this, and he says, okay, let's take this little bit of wire here, and let's just say right in this area there's a little electric field. Now, the electric field may be stronger back here or maybe weaker over here. Who knows? But maybe for the simplest conversation, we just should say it's the same electric field throughout the wire. Okay. But what often happens, he noticed, is that the electric field is proportional to how much current you get in that small area. So let me pause here. This is what I'm going to call a current density. It is the current per area. You might write this as I over A. Oh, I just remembered, did I use the symbol I for current for you yet? Oh yeah, okay, I guess I did here. Okay, so current is the, or I is the symbol we will use for current. And this symbol, I'm not sure if you are familiar with this symbol. It's one I'm going to borrow from math. Have you guys used proportionality? When you say something is proportional? Okay. So this is what I'm going to call the microscopic version of Ohm's law. And what I mean by microscopic is, of course, I'm looking within the wire. I'm looking at a small piece of the wire. So I'm not looking at the whole voltage of the whole wire yet. Many of you, in fact, all of you, did a lab on Ohm's law. And we're going to build up to that. So I don't want you to confuse what I'm saying now, which is what we'll call the microscopic version of Ohm's law, compared to the macroscopic version of Ohm's law. And that's what we did a lab on. And so let's build up to the macroscopic version. But on the microscopic version, here is Ohm's logic. With a couple of experiments, he tried this. He said, let's set this up. And he sets it up with some wire and some batteries, and he measures the current density. If he knows the electric field in this area, he says, how much current am I getting through that one little area? And so he gets a particular value. And then he doubles the electric field. And as I said earlier, what would you expect? Yeah, you would expect more current. And in his case, it doubled. And he tried it with different materials, and it doubled. And then he tripled the field, and the current density tripled. And so there seemed to be a pattern that occurred for every material. Now, did it happen all the time? No. So I want to emphasize that. I'm not saying that what we're about to discuss happens all the time, but it happens a lot of the time. And since it does happen a lot of the time, and it's the easiest one, usually proportionals are easier than more complex functions, this is where we start our circuitry. This is where we start our education in understanding what is current, what is resistance, how are they related together. Okay? And so this is where Ohm starts. He just notices that, hey, you increase the electric field, you increase the current density. In fact, you could write that as an equation. You could write it then by saying the current density would equal to some number times the electric field. And that number would be this proportionality constant, right? It would be some number that probably is not the same for every material. I wouldn't expect it to be the same for gold and lead and copper and zinc, and then I would expect them to be all different. And as we'll see, they are all different. But what I would expect, and this is the whole idea of Ohm's law, that if you set up this electric field in copper and then double it, you get twice as much current density in copper. If you set this up in carbon, and then you double the electric field, you get twice as much as you had before with the carbon. But the carbon does not have nearly the same proportionality constant. So they're different for the different materials. In fact, it's because of that we should probably give this a better name. Let's not call it the proportionality constant. What would be an appropriate name then for that symbol? How about conductivity? Does that make sense? And so I think you know that. We do this a lot. You did this a lot back in Physics 121, right? We said let acceleration be a constant. How do you get velocity? We integrated. There was a constant of integration. We didn't just leave it as a c, but we studied the equation and said, let's give it a name that will have some meaning. And we said, well, the meaning of that name would be initial velocity. I don't know if you remember all that, but I'm just doing the same thing here. I'm saying, look, if we make an experiment and we see that doubling the electric field doubles the current density, then it's got to be an equation with some proportionality constant. And we should probably then give it a name. And that's what we're going to be talking about. We'll give it a name. We'll call it the conductivity of the material. So as I was saying, copper would probably have a much bigger number than carbon because it conducts much easier. That means for the same electric field, you get a higher current density in copper than you do for carbon. Fair enough? I do want to point out, I'm using that little symbol sigma. Didn't we see sigma before? What did we use it before? Yeah, we used it for a surface charge density. And so I just want to make sure I point out that I am not talking about that, even though it's the same symbol. Okay? So that's unfortunate, but hopefully you'll be able to tell the difference between them based on that idea of the context of the discussion. Well, like I said, if this is true, then we say the material is ohmic. We say it obeys Ohm's law. We say if you double the electric field, you are now going to double the current density. However, I must admit, this is not that useful because it's on a microscopic level. It's great in a theoretical discussion. It's great when we're drawing little pictures. It's great when we're trying to get the students to understand what is happening on a microscopic level. But I think most of you know when you actually then go into the lab, and the labs we have done so far, and you go to hook it up, you don't measure current density. What do you measure? Yeah, those little machines, the ammeter, they measure the whole current that's going through the wire. So we should probably switch this. And we have voltmeters. They don't measure electric field. They measure voltage. So we should probably take some more steps to get to bigger things that we can measure in the lab. And that's going to be the more useful one. That's what I'll call the macroscopic Ohm's law. And much more useful when we go doing our calculations and our measurements.
Was this always true at the microscopic level?
No, it's not always true at the microscopic level. It is often true on the microscopic level. Yeah, yeah. So your simplest materials do this. Yeah. But not all materials. Okay, so moving on, I would probably say, all right, here's current density. And I introduced current density back here to say, look, what current density is the current per little area, meaning that it could change within the wire. But if I replace current density with the total current divided by the total area, and I replace electric field, and the electric field, your author, I think, does a pretty good job in this picture. Maybe I should write out the equation again. But if you remember, the change in voltage was negative the integral of E dot dr. If the electric field is a constant, and so for simplicity, let's just say it's constant, and it pretty much would be the same constant. If this was a wire that had the same material, the same thickness, I kind of would expect it to be the same all the way through. But don't we get the change in voltage to be the electric field times the length of the wire? And so that's why your author put electric field. He put the voltage between these two as A to B, and then he puts the length L here, so that he could come over here and say that the electric field is the voltage between those two ends of the wire, A to B, if you will, and then the length. Now let me rewrite this equation. And now you will probably recognize it more as the equation you saw in labs. Ohm's law on a macroscopic picture. I mean, here's what this is saying. This is saying current equals that, right? You might like to write it this way. Voltage divided by, and I guess we divide it by the reciprocal, length over sigma L. Because now I'm hoping you get some insight from here of what resistance is and where it comes from. All right? And so that was the whole point of this discussion here, is to say, okay, what is actually stopping these from flowing? And you can kind of see now, after we've done a couple of steps, if we call all three of these factors R for resistance, what do we have? We have current is equal to what? V over R. And I'll put a box around it, maybe a second box, because that is really what we're trying to get to the end of this chapter on, is Ohm's law, the macroscopic version of Ohm's law. That it is saying this: what determines how much current is flowing? Can you see it? What determines how much current flows? A, how much are you pushing it? The voltage. That, I think, makes sense to you, right? More voltage, more push means more current. Then this number down here would be the resistance, right? If this number is big, what would happen to the current? Yeah, it would go down. So this number in the denominator is a measurement of how much does it oppose the current. And so I like to think of this as an analogy with Newton's second law. When we did our mechanics, we said what would determine the acceleration of? And we would have an object here. Okay, and so if this is a box, you would say, okay, what determines the acceleration of this box? Well, more force would give it more acceleration, right? But what else would affect the acceleration? Yeah, less mass would give it more acceleration, or more mass would give it less acceleration, right? And so we had two factors that went into play to determine what is the acceleration of the box. One was how much are you pushing it, and the other one is how much are you resisting it, right? And we really have the same thing, okay? How much current actually flows? It depends on how much are you pushing it and how much are you stopping it. You put the two together to figure out how much flows. But I think the derivation in this gives you a little more insight. Do you see these three factors and why there is stoppage? I mean, one of those is what? What was L? Yeah, how long is the wire? When I left you on Thursday, I was showing you this kind of silly demo where it says, imagine this is the wire here. Imagine the wire right here, okay? And this is supposed to be the cutout of our little wire. And these nails are supposed to represent the little atoms that are in the wire. And I think you can see that if I take these little plastic balls here and think of these as the electrons, can you see that as they are being pushed through, and I'll just use gravity to push them through, but as they are being pushed through by a voltage, they are being stopped. Stopped by what? Well, one of the factors is how long is it, right? Can you kind of see that if this board was longer, wouldn't it be harder to get through because you have more nails to hit? Exactly. And so one of the key factors into the resistance is how long is it? The longer it is, the more of these little pieces and atoms that you're going to hit. Okay? But that's not the only reason there's resistance. Clearly, there's another factor in here. What was A? Area, right? And that one I think might be a little bit harder to see. But when you put a bunch on them, you can kind of see, if you try to crowd a bunch of electrons through here, do you see how they run into each other and they bump if they get crowded? And so the smaller the area of this wire, the harder the harder it is for them to get through. And so this right here is a measurement of that resistance. And so you can see the area is in the denominator. Small area means lots of resistance. Just like long wire means lots of resistance. So if you don't want a lot of resistance, oftentimes we don't want resistance, sometimes we do want resistance. But if this is just a wire that is trying to deliver power to something, I don't want a lot of resistance. So if this is, say, an extension cord, what might be the best extension cord I could use? The shorter the better, right? And the fatter the wire, the better. Fair enough? And that's going to give me my least resistance. In fact, a good example of this was a few years ago. One of our students was, he worked for Home Depot. And we had this discussion. And it was great. He put it together and you know, came back with this great story. He goes, oh, you're not going to believe what happened this weekend. He goes, Friday night, we set up a new display for a vendor. And what it was are you familiar with the air guns, the pneumatic air guns that shoot the nails in? Yeah. Okay. Well, this wasn't pneumatic. This was electric, okay? And so it had a plug, and you plug it in, and it used the current, and what we'll learn later on, a magnetic field, and it shot the nails out with a magnetic field. And so instead of using air pressure, it used current. Anyway, so they hook it up one evening to go on to display Saturday morning, and so they put it right in the front of the door, and they put a bunch of wood, and they put this out of it, and the customers were supposed to walk in and try this new gun, and there's the wood, and they're going, oh, let me give it a try. And so they'd put it on there, and they'd pull the little trigger, and the nail would only go halfway in. Halfway. Halfway. He said every customer looked at that and said, well, that sucks. And then they go on and buy a numeric air gun and leave the store. And say, well, I'm not going to buy that one. It doesn't push hard enough. And he too, he said, I started wrapping it up, I put it in the box, we were going to ship it out Monday night, send it back to the vendor and say we don't want to carry this product. And then he got to thinking about this. He goes, wait a minute. And he looked carefully at how they had set it up. And they had an extension cord that was wrapped around the base a good 100 feet, plugged into another extension cord that went up to the ceiling, plugged into another 100-foot extension cord that was plugged in the back of the building. So they had 300 feet of extension cords. And he goes, you know, I just wonder. And so he unplugs it. The extension cord that came with it, it was about 3 feet long, and he plugs it directly into the wall socket, and it just shot the nails all the way in, every single time. So they reset it up, and customers were more happy, and it seemed to work. It worked really well. What was the problem? Too much resistance. Too much resistance because they had 300 feet of extension cord connecting to it. I noticed on my air compressor the same thing. That my air compressor sits here. It's got a cord on it that's about 6 feet long. It's got a little tag on the end of it. It says, do not use extension cord. Which, something like for that is just begging me to go, well, I wonder why. So I get out the extension cord and I plug it in. And interesting enough, it would not turn on. I mean, I could plug it in straight to the wall and turn on my compressor and it would just... But when I plugged in the extension cord and I plugged it into the wall, you know, a 50-foot extension cord, you turn it on and it goes, you know, and then it just would not turn over the motor. And so it was very clear that the engineers designed this and knew it needed enough power. Now, most equipment, fortunately, don't need full power. So if you run a 100-foot extension cord, you know, to run a weed whacker or a chainsaw or something, usually they still run. You may not even notice they run with less power. But my point here is, as we try to get an understanding of what resistance is, any of these factors contribute to the resistance, and one of those is how long the wire is. And so something that needs just enough power to operate from that plug, like an air compressor, or apparently like this gun, this nail gun, you can't add any more resistance to it. On the other hand, as I said, my chainsaw is a good example because I've run a 100-foot extension cord from my garage out to the backyard and say, okay, I'm going to cut down this old tree here. But I've noticed the chainsaw not working that well. Maybe I should just go buy a gas one, but you know, okay, but it's got what's another alternative to get more power out of this? Even if I still want 100 feet, what could I do here? Yeah, you know, you say better extension cord. What do you mean by that?
Better materials.
Less resistance. How do I get less resistance? Yeah, make it thicker. And so you'll see that when you buy it, you'll have like an extension cord that says 16 gauge, which are pretty narrow. And then 14 gauge. Well, they're a little fatter. Even though I know the number gets smaller. But they're a little fatter. The wires are a little fatter. They cost a little more. And then you'll go down to 12 gauge, and that's pretty fat. It's about as fat as you can get it. There's really no point in going less than that because the wires in your wall can't do more than that. But now you can get the 12 gauge, and that's a lot fatter and a lot less resistance. And I notice it a lot on the difference between my nice, as you called it, extension cord, which is 12 gauge and 100 feet long, and although it's pricey, but my other extension cord, which was real cheap, and so I got lots of them, is only 16 gauge. And if I try to run off that, it doesn't work well here, and it's all the thickness. Now, I think you were going to say, if I'm not, I'll take your question. But wouldn't it matter on the material? Yeah, but they're all made out of copper. Copper is not that expensive, and they're all conduct really well. So yes, I should make it out of copper, and that would be a little bit better than aluminum, let's say. But I don't think anybody makes it out of aluminum anymore. I mean, wires out of aluminum. If you have a house that maybe is more than 40 years old, you might have aluminum. 50 years more likely, but all the wires are copper. Just too easy to get copper.
Is this the primary reason why like long range power lines are just high voltage instead? Like they don't like try to make the wires bigger, they just up the voltage as much as possible?
Well, you do want to
'Cause then you have
That's a little more complicated. I tell you what, let me get to the end of the lecture and I'll address that one.
Yeah.
In fact, yeah, you have a good homework problem like that. Yeah. Yeah.
Can you simplify the current equation? So you know change the voltage is E times L. And then
Okay, voltage is E.
over here you change the voltage is E times L. Can
Yeah.
you plug that in back into the equation for the current?
Oh, sure I could.
And like get E like
Wait,
E.
you want me to plug it back here?
Yeah, I was just because the L's would cancel. I was just
Oh yeah, but if I plug it back in, that's where it came from, so I end up with this. Yeah, sure. So if I plug it back in, I get to here. Yeah, so Ohm's law on a microscopic view or Ohm's law on a macroscopic view. But as I want to emphasize here, as we try to understand what is current and resistance here, is that this, I think, is easy in your mind to understand. Doubling the electric field, you double the current density. But after a few steps, you lead to this. This is going to be more useful to us. This is the macroscopic rule. These are the things that we can hook our meter to. This is what we'll do in the lab. We will measure how much current, we will measure how much voltage, we will measure how much resistance. And what I want you to see in this step is that the amount of resistance then has reasons, right? Even though when we do a lot of these problems, and especially you guys who are probably in the circuits right now, you probably just say, oh, the resistance is. Now, you don't know if the resistance is because it is long, or because it is thin, or because it's made out of the material. You've just put it all together in one big clump and said, this is the resistance. Okay? And we'll do a lot of that too, but that doesn't really help with our physics. Our physics is what is the cause of these of the resistance. And so that's what I want to put here. So the resistance is equal to the length divided by the conductivity divided by the area. And you see actually four factors there, and I want to talk about the fourth one. Yeah.
So if you had an extension cord that had like a kink in it, wouldn't that cause more resistance? And a better extension cord would be one that it would stay shorter?
I believe so. Yeah. Because and this overly simplified model kind of assumes the same electric field throughout. Now you start kinking it, the electric field has a gradient, if you will. Yeah. And you pinch it too much, you can have troubles. Sure. Well, let me do one more thing here. Let's define rho as the reciprocal of the conductivity.
Resistivity?
And let me pause there to emphasize. Have you seen rho before this semester? We have, right? What did we use it before? Yeah, we use this as a charge density, charge per volume. I'm not talking about that, okay? And again, maybe it's unfortunate we use the same symbols here because we use sigma and rho, but it's not the same as when we were doing Coulomb's law and we were using sigma for the charge per area and we were using rho for charge per volume. I'm not talking about that anymore, okay? I'm talking about something else. And what would you call this? It's the reciprocal of the conductivity. So isn't this kind of the opposite of how well it flows? Right? Didn't the sigma mean how well it flowed? I mean, isn't that why we called it the conductivity back here? It is saying that if this number is big, you can get a lot of current for just a little electric field, right? So this sigma is why we call it the conductivity. How well does it conduct? So what do you think we should call this? Yeah, this is what you might call the resistivity of it. Okay, notice I didn't call it the resistance, it's the resistivity of it. It is saying really how much resistance does the material have. It's the reciprocal of the conductivity. So whichever way you prefer to look at this, and your author, and I must say most authors, choose to look at how much resistance the material has, not how well it conducts. So I'm going to take one more step here and replace this with a rho, an L over A. And so it goes into the numerator there. And so what we say is, okay, what contributes to the overall stoppage, the overall resistance? Again, how long is it? Again, how thick is it? And again, what kind of material is it? But we'll usually label the material not on how well it conducts, but how well it resists, if you will. It's resistivity, okay? Now, I'm hoping you see 4 effects here of resistance. And I think 3 of them are pretty obvious, but I don't think the 4th one is so clear, other than we did mention it last time. I mean, when I say what causes resistance, clearly one of it is straight from the material itself, right? What is the resistivity of that material? In fact, your author does a great job of giving you a nice little table. Wouldn't surprise you that as you do the homework, you're going to have to look in this table and you're going to have to say, okay, what materials am I using? And so you can see a little chart here, and they label them from the lowest resistivity up to the highest one. So in other words, best conductors to worst conductors. So starting at the top, if I wanted something to conduct really well, you know, like an extension cord here, I'd make it out of silver. Well, it's going to get pretty pricey, make it out of silver. So although it's great material for conducting, probably don't want to actually sell one out of silver. So we'll drop one down to relatively inexpensive metal, copper. And so, as you mentioned, you know, they're all just made out of copper. But you can go see the resistivity as you go down. Gold would be next. Aluminum, that was my question. You know, I commented earlier that many decades ago, it was a little more expensive to get copper, and a lot of things were made out of aluminum instead of copper, but we got plenty of copper. And then tungsten, iron, and you can go on down the list. But the point is, this would be the resistivity of it. And so if I had this long extension cord and I wanted to know what's the resistance of it, I would, of course, take the resistivity of it. And then how long is it? And then what is the cross-sectional area? And that would give me the resistance of that material.
So do some of those perform, I mean, does the order of the list change based on temperature?
Oh, now, okay, hang on with that question, because you threw in the word temperature, and that's what I want to build up for. Right, so you probably noticed the 3 obvious ones. That the length of the material affects it, the cross-sectional area affects it. So these 3 are very clear. What's the 4th one that affects? Yeah, and it may not be so obvious because temperature is not listed directly in that equation, but yes, that is one of them. The mental picture I tried to give you last time was this. The 3 are easy to see. How long is this? How fat is it? The nails represent the material, so how often do you hit them? If they are silver, I obviously hit them only a few times. But if we go all the way down to carbon, they hit them a lot of times. And so the atoms themselves, the material themselves is important. But why does temperature also come into play here? And yeah, this little example doesn't show it real well. What's happening to these atoms? Aren't they moving around, vibrating? Isn't that what temperature is, these moving atoms? So if you could imagine these with them moving, what do you think might happen if I warm them up? Would they move more? And then the chances of hitting would be even greater as they took up more space, right? And as they bounced around? And so it doesn't surprise you that temperature comes into play here. And so more temperature will also give me more resistance, with a few exceptions, and we'll talk about that in just a second also here. But in general, the more temperature, the more I get the resistance. So your question was, what is this number? And so you got to look carefully. This number is listed at 20 degrees. So these are the kind of numbers you would say if you are hooking it up in the lab. a lab's usually 22, 23 degrees, roughly 20 degrees. So if I wanted to know the resistance of an extension cord, I plug it in here and I plug in this little lamp for the overhead. If I wanted to know the resistance, I need to know the resistivity at that temperature. And since it's in the room here, it's probably 20 degrees and I can use all these. But will they change if the temperature goes up? Oh yeah. And that's what the second column is for. This second column is really telling you how much it changes every degree you go up above 20. Or how much it goes down for every degree below 20.
You mean how much temperature it changes, not how much the room changes.
Say that again?
It's the temperature inside the material that matters.
Oh yeah, it is the temperature inside the material. Fair enough, because it could be warmer than the room. Is that what you're getting at? Yeah, yeah. All right. But it's the temperature of the metal, of the conductor, or whatever, you know, semiconductor, whatever is flowing the electricity. So we like to take one more step here. We like to write it this way. The resistance is the resistivity at 20 degrees, and so this rho naught is what this first column is. This first column is telling you what is the resistivity of that material. Let's say glass, which is really high. Maybe not a good example. We'll go lead. Nichrome. Nichrome's a good one because it's one that does conduct, but not very well, and so we use it a lot. In fact, you guys who did the 2-meter potentiometer already, that wire there was the nichrome. Okay, and it's kind of nice because it does flow, but also has a significant amount of resistance. Your toaster ovens are often made out of that, so that they'll glow red hot in there. But the point being here is this is what I would use for rho naught, but then what's this number? This number is what we call the temperature coefficient. It is telling you how much the resistivity increases for a change in temperature. So it would be 1 plus, and the symbol we like to use is alpha, and then multiply by delta T. Okay? And so that alpha is this part of your table. See, it says alpha there. This is telling you how much the resistivity would change. Okay? And again, so just to make sure I summarize this really well, do you see what resistance is? Do you see how resistance is the stoppage? Do you see there's 4 factors? It's length, it's area, it's material, and it's temperature. All of those are stopping them. Yeah?
So you have resistance equals in the resistivity time. Shouldn't it be resistance and then the resistance amount? Or like you have capital R as resistance.
Yeah.
And then on the rho naught, is that the resistivity?
Yeah, that's resistivity.
Okay.
So this would be so this is the factor from the material. This is the increase of the resistivity due to the temperature. Then this is the length and this is the area. Let me go all the way back there, yeah.
Is the conductivity or the electric conductivity related to the heat conductivity of the material?
Oh, yes, but not exactly perfect one-to-one. In other words, you're there when we throw out the word conductivity. There's really, how does it conduct electricity? That's what we're talking about. And you're bringing up, how does it conduct heat? Okay? And the heat part of it is kinetic motion of the particles. Those can come in part from the electrons, which is the conductivity. So that's the part where conductivity of electricity and conductivity of heat are a one-to-one match. And so when one increases, the other one increases. However, conductivity of heat can also occur by one atom bumping into another atom without electrical particles moving from one to another. So thermal conductivity has 2 causes. One from the moving in electrons, which is the same as the electrical conductivity. So that's why often they go hand in hand. Good electrical conductors, like copper, are also good thermal conductors. But it's not the whole story, because thermal energy can be conducted by atoms hitting each other. Diamond is a good illustration. Diamond, the electrons are so tightly hooked that you don't get any conductivity, electrical conductivity from diamond. But you get an excellent thermal conductivity, because the bonds are so strong that when one atom barely moves, it pushes the next, pushes the next, pushes the next. And diamonds have an excellent thermal conductivity without an electrical conductivity. So I hope that illustrates my point. In fact, for whatever reason, it reminds me of a very stupid movie. Was it The Congo? Anybody see that? Well, I mean, what was the theme behind all that? Right? What were they trying to do? Why were they trying to get the diamonds? To make better lasers. Why? They were trying to cool the laser without introducing electrical conductivity. So that was the science behind it. How are you going to cool the laser without having electrical conductivity? So by having the material made out of diamond, they were going to get the high thermal conductivity without the high electrical conductivity. And they didn't explain the science very good in the movie. Maybe it's just as well, but that was it. So the whole battle stuff was all about the diamonds, to build the laser, to get the laser to cool.
Are these related to the dielectric charge?
And there is a relationship to the dielectric constant too, but again, it's not a perfect connection. In fact, when they become good conductors, we should probably just throw that away for altogether, because the dielectric constant is really a number we want to talk about in terms of insulators. Okay, and so if these things get more like insulators, like glass, then there starts to be a better connection between them. But when you start talking about copper, which is a good conductor, you don't usually talk about its dielectric constant. You can, but not usually, because it doesn't really make sense. You're not using it as an insulator. Copper's a good conductor. Yeah.
Is there like a way you can estimate maybe these with the lattice structure for the material, or is it kind of a ballpark range and then go make it?
Oh, no, well, no, there's a lot of theoretical work that is based upon, as you said, what the lattice structure. Is this and I'll use a word you may or may not heard, but how the atoms lined up in a cube. They could be face center cubic, or body center cubic, or simple cubic, or many other combinations. And so definitely the structure of it is related to this. And so, yeah, you could theoretically calculate this. And many of you may find yourself being in the field of theoretical physics and theoretical engineering and trying to calculate it and trying to figure out what new materials could I create to lower or increase the resistivity. So those are great, discussions. And but in our case, we're not going to get down to the material science at this point. We're just going to say we go in the lab and we measure it, and that's the number, right? And now we have that number, and we're going to use that to build our product, right. But understanding where that comes from is, of course, another interesting part of material science, and one that wouldn't surprise me if you or others found themselves interested in that field and working in that field. Yeah.
Though the temperature coefficient is like experimentally found, does alpha at high enough temperatures take into effect that like the wire, the material will expand at like 200 degrees?
Yeah. Okay.
Celsius?
Now again, maybe what you're saying. Don't take this as too literal. This is an experiment, okay, and it changes in a linear fashion only over to a certain extent, right? And so this is, if I can use a math term, the first term in a Taylor series, right? The resistivity would change with temperature, and it would be, the initial, then it would be some factor, then the change in temperature raised to a power of 1 times some coefficient, which we are calling alpha. But then there would be a beta, and then it would be squared, alpha, beta, gamma, delta. That would probably be what is really going on. And what we often do when things get real complex like this is we say, well, this is approximately true, and that's what we're doing right now. Okay, so if you're not going to go too far from 20 degrees, if you're just going to take this wire and drop it in a bucket of ice, that's only 20 degrees. Yeah, then it's probably very accurate. But if you're going to try to take that number and go all the way to 10 Kelvin, it won't work. You won't get the right number when you try to change 300 degrees. Yeah, yeah. So it's a good first order approximation. Yeah, yeah, yeah. So not a complete story, but a good place to start. And as I think I've mentioned a few times, it's where we need to start as we get, familiar with our physics for the first time. And then this is your first year. Then you'll have a second year and a third year and a fourth year, and and each of you will focus in a little narrower spot.
So what material are the superconductors made of? With zero resistance. Oh, they're super cool.
All right, so let's see if I can build up to that question. You can kind of see then, two more things I want to show you with this resistance. Let me build up to what you're asking about, what is called superconductors. Okay? And for those of you who may not be familiar with the word superconductor, the reason they are given that name is because some materials, for reasons, hopefully I'll get somewhat of an explanation, not a complete explanation by any means, but a somewhat explanation here, is that they, surprisingly, their resistivity actually goes to 0. Not approximately 0, but literally all the way to 0 as you cool them down. They don't just get smaller and smaller and smaller, but they actually get to 0, which is an interesting phenomenon. But to understand that, let me take a couple more steps here. Okay? And to those couple more steps, let me change the picture back here. Let's go back to this picture that we were looking at earlier of what might be happening on a microscopic level of these things bouncing around here. And so if I kind of do a little bit of mechanics, these movement of these electrons. If I were to put on the board A equals to F over M, hopefully you would remember that, right? That's Newton's second law. And really that's essentially what's going to happen, right? On a microscopic level, what I am doing is applying a force to this electron and it starts to move, fair enough? And so the force that I am giving this electron, or if it's not an electron, it is some charge Q. So I'm going to put the charge Q, the symbol Q for charge, because it may not be an electron. If it is, then I know its value is 1.602 times 10 to the minus 19. But let's just say whatever this is, it has a charge of Q, then the acceleration would look something like this. Let me also remind you of this equation. Final velocity is equal to initial velocity plus acceleration times time. You remember that one? Okay, that was a great equation that gave us velocity. Now I must admit, that equation was only really true for constant acceleration, wasn't it? All right, so we're going to play with that a little bit. And so what we're going to come up with is probably not a perfect exact equation, but something that's kind of reasonable here. And here's what I'm going to say here, is what I could kind of do here is the acceleration probably has a changing acceleration every time it makes a hit. I mean, look at this picture for a moment. Look what might happen between collisions. As it is moving between collisions, it is only being pushed by the electric field. Fair enough? And if that electric field is pretty much constant in that little microscopic area, then I would say we do have a constant acceleration between collisions. Although once we have a collision, whoa, then the acceleration could be really large or small depending on how the collision occurred. Okay? So I am not saying that this electron has the same acceleration for all time. It actually has it a constant for a moment in time, right? Then it has a collision. Then it has constant for a moment in time, and then has a collision. Okay? And so that's why I put the little bar over there. And maybe I should ask, do you remember what the little bar means? Yeah, average. So let's just say this is kind of that average acceleration during the intermediate, during the collisions for it. Because then if I say, well, let's just look at the average. Because I got to admit, this is going to be pretty complicated. I mean, I'm going to have all kinds of crazy motions going on, that there's going to be collisions going on. Some of them will occur early, some of them will occur late. Unfortunately, there's a bunch of them. So when I say average, it can get pretty accurate, because some of them will be below the average, some of them will be above the average. So I'm not saying every single one does this, but that's kind of the neat thing that makes statistical mechanics kind of nice, is you don't have to focus on every single one. The overall effect is the average anyways, and so some will go a little faster, some will go a little slower. But if I solve for the average of one of them, that's the equivalent of what's happening when all of them occur, just some go fast and some go slow. And so that's what I'm going to do. I'm going to think about one and look at the average of one. And then start writing this down. Now, I'm going to start here with what I might call the average initial velocity. I mean, think about this electron when it makes a collision. When it makes a collision, I bet sometimes it hits and bounces in the negative direction. Fair enough? I bet other times it kind of just goes by and does a grazing on it and really doesn't slow down at all. I bet other times it hits it and kind of ricochets up. In other words, it can ricochet in almost any direction, right, when it hits this big atom? So what do you think my average initial speed is? Would it be fair to call that 0? And so there's step one. If after every ricochet, there probably has an average speed of 0. Some of them, like this one, gets ricocheted down. Then this one gets ricocheted up. This one gets ricocheted back. There's probably an equal number of ricochets that are back and forward. There's no reason to suspect maybe one versus the other. So I'm going to say that after a collision, probably the average speed, if I take 6 billion of these, is 0. Some are still going that way, some are going that way. The average of left and right is 0. So I'm going to put a 0 there. And then I'm also going to put this QE over M for the acceleration. At least this is the acceleration between collisions. And so if I put then the average velocity between collisions as QE over M times T, and I'm just going to put a little average there. Let me pause to make sure you see the mechanics of it. What am I really saying here by this average time? The average time between collisions, right? Okay, so what's going to happen is it's going to move a little bit and then collide, and then move a little bit and collide. And so this should represent something along the average speed between them, right? I'm not saying it's its total speed in any way. But do you remember that drift speed? Isn't that drift speed the average speed? Right? Isn't that what is making these things move? So even though they ricochet and go all kinds of different directions, it is this drift speed that is what this comes out to be. So if I make that connection, I can put V sub d for the drift speed. And this becomes a QE over M. And your author uses the Greek letter tau to represent this average time between collisions. So let me get rid of the T with a bar over it and just call it a tau. This is the average time between the collisions. Now, I suppose you're wondering, why do I care about that? Well, do you remember an equation that got us started Q, yeah, that got us started about an hour ago, right? It's one that I put back on the board. I derived for you last time that said this would be the current in there. Let me put the A to this side. That's current density, right? And when we started this discussion on resistance about an hour ago, we said the microscopic view was this conductivity divided by, or multiplied by E. And if I put these two together here, watch what happens. This current density would be N V D Q, so that's current density. That equals sigma E. If I then take what I just derived for the average current density, our drift velocity, I get Q E tau over M Q equals sigma E. If I rewrite this, I get N Q squared tau over M times E sigma E. Now I know that maybe seemed like a lot of work and it was going back to our mechanics, but here's why. I wanted to give you some insight. Some insight into really kind of what you were asking earlier theoretically is, could you predict what the resistivity or conductivity of the material is? Do you see that it's these group of numbers that would be equal to this conductivity of the material? And so what I'm really saying here is the conductivity of the material is really based on these factors. And the most important one I want to focus on was that tau. What was tau again? The time between collisions, right? So what if the time between collisions is very long? Like 500 billion hours. I know, it was a little extreme, but what I'm getting at is if this number is big, doesn't that say the conductivity is big? And so I'm trying to give you some insight to that chart that is now gone. I should put it back here. But this chart tells us something important about the material. What this is telling us then, as these little electrons go through silver, the chances of them hitting a silver atom are pretty small apparently. The collision time is very long. And the whole reason silver conducts better is we don't have the collisions. Okay? Where on the other hand, if we go down to this nichrome, the resistivity is much higher, that is the conductivity is much lower, which means the collision time is much lower. And the reason then nichrome is not a very good conductor is because the time between collisions is not very much. Do you have a question?
Yeah, what's N?
Oh, now there are other factors up here. And I do want to address those other factors. And I'm glad you asked what N is. But before I even get there, let me just review there. Did you catch that? That's the whole point of this discussion. The whole point of this discussion now is when you take a microscopic view and you say, okay, the big picture is all of our material have resistance. When you break that down and say, why does it have resistance? You have to say, well, it has resistance because of those four factors. What is its temperature? What is its material? What is its length? What is its area? Now if you break that down and say, why does the resistivity or the conductivity change? Now you can begin to see it that it's the collision time. And if this collision time gets smaller, which is what happens when you warm up your piece of metal, then what you will see is that the resistivity all increases. Ooh. With the exception of a few, the resistance decreases. So let's talk about that. That's why I wanted to derive this. But the most of them, what ends up happening here is that the collision time gets smaller because now the atoms are vibrating much faster, and for those electrons to get through, it's harder, and they collide in a shorter amount of time, right? Now, if you will notice, there are some materials, such as carbon, silicon, germanium. All of our semiconductors, actually, is what it turns out to be. They have a negative coefficient. Ooh, now, first of all, what does a negative coefficient mean?
Better with more space between atoms so the electrons can flow faster.
Okay, well, okay, don't quite go that far, but just, and I'm not even going to say that, that's right, but don't go that far. But what do I, by having a negative coefficient, if I take that material and warm it up, what's that say?
Conductivity increases.
It conducts better, right? So when I said earlier that the materials increase their resistance when they increase their temperature, that was only partly true. There are some materials where that does not happen. And the reason for that is buried right in here. Do you see it? It's the N. This was your question. What does N stand for? What was N? We derived it way, way, way back on last time. What did the N stand for? It was the number of particles that were flowing in our circuitry. Okay? So here's why certain things, like copper, can actually become better conductors when they get warmer, is that when I have an atom and I warm it up, aren't they hitting each other? And if they hit hard enough, couldn't they bump off electrons, making those electrons free to flow? And so all of our semiconductors, I think, are very interesting, because even though you're warming them up, and in the process of warming them up, you reduce the collision time. That is, those electrons actually hit more often. That number gets smaller, but this number gets bigger. And this number gets bigger at a faster rate than that one gets smaller. Now, the reason you don't see that for copper or for silver or for gold or for aluminum is because those electrons are almost all free anyways. So if you warm them up and hit them even harder, you don't get more charges flowing. This number really doesn't change for copper and aluminum. But for your semiconductors, the whole reason it's called a semiconductor is because only a few of the electrons are actually able to break free from the lattice structure themselves. And so when you warm them up, you actually increase that number. And if you increase that number more than you decrease this number, it's actually going to end up conducting better as it gets warmer. And so that's why these guys end up, and all of your semiconductors, end up having a negative coefficient. And they actually conduct a little bit better. The consequences of that is absolutely interesting when it comes to electronics, because most of our computer chips are made out of silicon. So, interesting enough, if this was not made out of silicon, it was made out of, say, nichrome, and you built a circuit out of nichrome, and something goes a little wrong, and too much current starts to flow, what's going to happen? It's going to heat up. And then what happens to the resistance of that nichrome? It increases. So what happens to the current? It goes down, doesn't it? But if it's made out of silicon and something goes a little wrong and it starts to get a little warm, what happens to the resistance? It goes down. And what will happen to the current? It goes up. And if the current goes up, it starts to get even hotter. And if it gets hotter, what happens to the resistance? It goes down. And what happens to the current? It goes up. And it gets even hotter. And if it gets hotter, what happens to the resistance? you can see this as a runaway loop. And so once something goes wrong with our diodes, our transistors, our integrated circuit, the whole thing just fries. It just, as soon as it goes wrong, just catches on fire. No, hopefully it won't catch on fire and burn the whole house down. But the thing just burns out because of the silicon. So you might say that your other materials are self-correcting for little mistakes. The silicon is not self-correcting, and it's a runaway failure. Once you have a little failure, it just gets worse and worse and worse, and this quickly heats up. And the more it heats up, the better it conducts. So the more it heats, and eventually it just melts itself down. So it's done. You plug it in and go, nope, that's fried. Recycle. Buy a new one, you know. So we don't fix our electronics. We recycle it, and that's an interesting consequence of this number right here. Now it just dawned on me another good point here, which I should have brought on a little bit earlier, but I heard somebody in the back there mentioning it too as I was scanning this. So which has a better conductivity? Copper or gold?
Depends on oxidation.
Well, okay, let's say at 20 degrees. It does depend on temperature. Fair enough. Doesn't copper work better? I mean, it's very clear that copper is ahead of gold. No, not by much. I agree. But isn't copper ahead of gold? So wouldn't copper make a better conductor than gold?
No, oxidized copper.
So yeah, why do we have then these gold-plated connectors? You know? Because why?
Gold doesn't tarnish.
Yeah, it's the surface of it, right? You only put gold on the surface. Copper, the whole wire, is made out of copper. And then at the end of the wire, you put a surface of gold. Why? Because if you left it as copper, and it was part of a connector, what happens to copper when it's exposed to the air? Yeah, it oxidizes. It becomes copper oxide, and that does not conduct very well. So you don't put gold on the end of these fancy connectors or platinum on the end of these fancy connectors because platinum or gold conducts so well. That's not it. It's the idea that they don't oxidize. And so they don't oxidize, and now you still have a pretty good conductor. I mean, look how good the gold is, right? And so that's the point of there. Somebody was asking about it. Yeah, copper, no, copper is a much better, well, I shouldn't say much better, but it is a better conductor. And so you're better off to have copper than you are gold. Costs a lot less too, yeah.
What's the more common material that they use?
For what?
For just the coating end of the wires that they plug in the next. It's a rubber, silver colored, but it's not silver. It's like a regular USB cable.
Yeah, I think it's just stainless steel. Is it something? I don't know if it's something special other than stainless steel. I just thought it was a stainless steel. Yeah. So it's a steel. It conducts. It may be not as good, but you're not going very far through it. It's just, as you said, the connector on the surface. But it's, again, a stainless steel, so it's not going to oxidize. And so it's much better than almost anything else you're going to put on there because it's going to oxidize on you. Yeah. Okay, well now, I think that answers at least your question, what is N? But the consequence of the N is very interesting, and that's, like I said, wanted to see it. And the consequence of the negative number is very interesting for you electrical engineers, and the consequences of your chips and how they're going to when and if they fail, how quickly they will fail. Oh, that's why statistically, you know, your electronics, usually, if you've ever happened to you, I mean, if you go buy a new product, electronic product, if something's wrong with it, it will go bad usually right away. If it doesn't go bad right away, it usually lasts pretty long. And so the electronics are pretty stable. They either go bad right away or they're going to stay working in their quote-unquote normal lifetime before they just wear out due to the excessive heat on them for a long period of time. Your other question, though, was about superconductors. You know. And so maybe I should say this, or maybe I'll ask it with a question. Can rho, which is a function of temperature, equal 0? And so, as we were saying, the resistivity of this material does change. But can it ever go to 0? Yeah, and there are some cases where it actually goes to 0. And so these are called superconductors, right? They have no resistance. Now, coming back to this equation, what would that mean in this equation? If you have no resistance, what would you say? What about collision? What? There's no collision. So what would you say about tau? Not zero. Infinite, right? Right? No resistance means infinite conductivity. It means the time between collisions is infinite. You never hit. Now, I know that sounds almost impossible. You're like, oh, that's crazy. And interesting enough, like a lot of things in science, this was first discovered by an experiment. And it's one for whatever reason. I just love the story behind this one, because it was a graduate student. And the graduate student went, and it was, I think it was lead. It could have been mercury, but I'm thinking it was lead. It was one of these two.
It was mercury.
Mercury?
Yep. April 8, 1911.
Oh, good. So mercury. All right. 1911. All right. Good. All right. So it was working with mercury, and the professor's instructions were saying, look, let's measure the resistivity, cool it down. So they cooled it down, and they cooled it down, and cooled it down. And you're talking about really cold temperatures. I mean, look at what we're talking about. We're talking about 4 Kelvin. Okay? So, you know, which is not an easy place to work at. You know, you usually put it in a bath of liquid helium, and you can't exactly see what's going on there because it's all surrounded by helium, and you're never quite sure what is going on. And I guess I like it because it reminds me of my graduate school days. I remember doing the same thing, and we're doing this, and all of a sudden weird things would happen, you know, and you would go, ooh. Only to find out, well, it got so cold that the thermal contraction pulled your solder joint apart. Oh, darn. You know, nothing interesting other than it got cold, it contracted, it broke, you know. And so a lot of those things happen. And I remember many times going to my professor, I said, well, it's doing this weird thing. And he'd go, yeah, try it again, you know. Well, apparently this graduate's the same idea. He got all the way down, and he got it down to 4 degrees and actually measured 0 resistance. And I can just imagine, I don't know if this is the complete story, but I can just imagine the graduate student going to his professor and saying, it went to 0. Yeah, go do it again. And so he did. He did it again and again and again, and he's probably just shooing him back, yeah, go do it again. But at some point, they did figure out that nothing's breaking. We are discovering something bizarre, something new, something really not necessarily predicted, but there was dropping, and it would actually have no collisions. And so you can see here that after doing mercury, trying other materials, there's tin, there's aluminum, there's zinc, there's lead. What's that? NB? Nobilium? Yeah, okay. Of course, now there's some other mixtures of stuff. And so you can kind of see where technology is taking it. I mean, what is this? Mercury, barium, calcium, copper oxide? All right? But this is actually getting really warm if you call 134 Kelvin warm. It's still very, very cold. It's not like you're going to put it at room temperature or close, but that would be interesting. That would be obviously a change in the world we have today, because no materials with no resistance means a lot of neat things. Because one of the things is we make our chips smaller and smaller and smaller. You probably know this well from your computers. I mean, have you ever taken one apart? You see a fan sitting on top of it, right? There's usually a fan on the chip itself. There's usually a fan on the case itself. So the fan blows air into the case, and the fan from the air. And there's like 2 fans, sometimes 3 fans, one for the power supply too. And so you're running quite a few fans. Why? Because it gets hot. Why does it get hot? Well, because there's resistance, right? And so we can make things a lot smaller if we had no resistance. Another issue is all this electricity we generate. For example, here in Santa Barbara, I mean, we get some of our electricity from Hoover Dam. That's 300 miles away. You've got to send those over wires that stretch out through the desert. Fair enough? Half of the energy is lost in the distribution of electrical energy, just getting it to the users of the energy. Could you imagine if there was no resistance? all of a sudden you could have twice as much electrical energy supply in this country just by the change of that. So this would be a very interesting consequence, and of course many people are trying different things for them. And so this, I'll call it a holy grail. I mean, if you could find a material that would have no resistance at room temperature, it would be phenomenal. Or even something kind of close where we could just kind of cool it maybe with water, chilled water. This isn't so bad because this could actually be cooled with liquid nitrogen. And so we're kind of getting there, and that's not too expensive. These other ones are just, on a practical side, almost unusable. They're so cold. But why don't they have any collisions? Why do they have infinite resistance? Should be addressed. Yeah.
I was just going to ask, so when, like 100 years from now, when we're like really out in space a lot more often, so on the dark side of planets and moons and stuff, it's going to be a lot easier to create superconductors. Like if we're on the, like where there's no sunlight, it should be like the temperature drops down to like, I know like 100 Celsius.
Okay, good point. I mean, yeah, if you were building something for a probe that's going to be operating at these low temperatures, a good point. That it might not be so bad. I think I mentioned to somebody, my uncle, although he retired last year, but for the last 12 years, he's been working on the replacement to the Hubble telescope, the James Webb telescope, and unfortunately, the launch date, I think at one time it was 2008, and just keeps getting pushed back, and so he finally just said, you know, I just got to retire. So he was. I remember when he started the project, he goes, well, I'm gonna. In 2008, he was going to be like 65. He goes, okay, I'll retire in 65. And, well, now what is he? 69, and he goes, you know what? I just need to retire. and his part of the project is pretty much done anyways. But I say all that because they are launching this thing, and if you know anything about it, it's going to be out 1 million miles from Earth. And its operational temperature is 40 degrees Kelvin, or 40 Kelvin. Yeah. So maybe something, I don't think they're doing anything with that, but I see the potential there. However, that would be very minor. I mean, anytime you wanted your electronics in the space station where humans are, usually the temperature is a little bit higher. Yeah. So, and then usually if you're orbiting something, yeah, there is the cold side of the planet, but then there's the warm side of the planet. So I don't know. I'm sure this will come around, and as far as I know, NASA hasn't used superconductors and the coldness on any of their probes, but I could be wrong. I mean, I know it's cold on Mars, but I don't think it's even close to that cold yet. Yeah. Well, anyways, I wanted to draw a picture here because here's the answer to our question. Is something interesting can happen, but only if things are perfectly aligned. That's why the cold temperature is absolutely important. If you think about these as being the atoms, and think of them as not moving by very much, low temperature, so they're barely moving. If you had an electron that was kind of headed perfectly down the center, which I admit, it's got to be kind of rare to get perfectly down the center, fair enough? I mean, chances are, if it started perfectly down, there's going to be some uncertainty. And if there is a little bit of temperature, this atom can move a little bit closer, draw it in, and once it draws it in, it angles down and it has a collision. So even this probably would not be a superconductor yet. But what if I had another electron? And you might think of this then as a lattice within a lattice, where all the electrons are repelling out from each other, all the ions are pulling into each other, and if they're perfectly wedged, they can balance. And if there's a slight variation in one, it pulls the whole lattice and self-corrects it, as long as there's not too much of a vibration. And so that's a good mental picture of why these guys can form groupings and pairs of electrons and actually make it through without ever actually hitting it. And so that's our very limited understanding of what's going on. Now, I'll say that with a little bit of uncertainty. That seems to be the case of what goes on these lower temperature superconductors. Nobody seems to really know what's going on in those higher ones. And that is too bad, because I think when somebody does finally figure out what is going on, then they will probably be able to predict better ones. And so we're kind of stuck in this field. But again, I remember being a graduate student when a lot of these were discovered. It was right in '89. I mean, it was just a hot topic area, and anybody who had a lab that could measure any kind of conductivity was jumping on board. And I remember and what's interesting is these things at room temperatures aren't even conductors, they're ceramics. And they're like, whoa, that is really, really just kind of weird. And they cool down and they become superconductors, yet at room temperature they don't conduct at all. And so nobody really has a good understanding to it. But I do remember going in, we had this lab, and it was just a high pressure chamber. And we would just take really copper oxide. Forget all the other stuff for a second, but just the copper oxide, and we'd throw it in this chamber and just crank up the pressure and measure it, when it goes, and when it would be a superconductor, and its temperature would change based on pressure. And the logic being you were pushing the atoms closer in together. So then, when you actually build it, you dope it with certain elements that actually pull the crystalline structure together here a little tighter. That was kind of the experimental, it still is, as far as I know, the experimentalist approach. You put it under a bunch of pressure, you see what is the best distance between them, and then you try to find the right kind of atoms that you add to your copper oxide that will pull them together without having pressure on them, and see what you get. So apparently they got 134 and could even be higher now.
Is that the temperature it has to be, or can it be those numbers or anything lower?
Anything lower, yeah. That and lower. Yeah, and it's superconducting. Well, anyway, and I didn't necessarily want to spend too much time there, but it is really interesting, and the future, and that's probably good for you guys to hear, the whole idea of the silicon and the whole idea of the other materials getting closer together and the whole idea of superconductors, because I think this is the kind of world obviously you will be leading into, what kind of materials that take place. Well, all of this then should be shown in a kind of a grand finale. I kind of skipped over it. Your author gave it first here. And now I think you've got this whole idea of resistance, okay? And the idea that the resistance is coming from these electrons that are hitting, that's the material. It's also coming from the length, it's coming from the area, coming from the temperature. And so we've got our resistance. We've got our voltage. Together that makes our current. And so, now that I've done all what I'll call the tiny, tiny stuff, the microscopic stuff, and you see what's going on underneath the wire, let's come back up to the macroscopic world and put then the result of all of this and just emphasize that this is the grand conclusion of this chapter. It's the same as the lab, that current depends on two factors. What are they? How much are you pushing it? How much voltage? And how much you are stopping it, right? And of course, the stopping part could be because of length, it could be because of area, it could be because of material, it could be because of temperature, right? So there's a lot of things that go in there. But as I jump back up here and look at this, I should probably talk then more about the units. We already mentioned this earlier. What do we measure current in? Amps. What do we measure potential in? Volts. And the one I haven't mentioned? Yeah, and so we give this a name in honor of Ohm, who worked this out. And so we will measure our resistance in ohms, and the symbol is the Greek letter capital omega. Okay? And so we will say things like the resistance is 1,000 ohms. Or if it's a small resistance, it's 5 ohms. Or maybe a lot more resistance, 10,000 ohms. Okay? And again, you saw that at the lab last week and the lab this week, although some of you still have to do the lab today there. But that's the resistance. And in fact, I grabbed some resistors. Okay? Here's what a real resistor would probably look like. In fact, I'll grab 2 and send the rest around here. And so in this resistor, it could be made out of a little wire, say nichrome, that is really long and thin, but it's kind of wrapped around in a circle, and then they put a ceramic around here, and so that determined its resistance. It's really long and thin, but it's made out of nichrome. On the other hand, instead of being made out of nichrome, maybe it's made out of carbon. And so most of its resistance is because of the material, not because of its length. And so if it's just one solid piece of carbon, you can see it's not very long and it's pretty fat. But because it's carbon, it still doesn't conduct very well and has a lot of resistance. So when I get the final end product, this is what it looks like. It is just a resistor, and the resistance comes from those 4 factors I was trying to point out here. And then, to know its value, we color code them. Okay? So let's mention the color code. Truth be told, we don't do much with the color code in this class. We kind of wait for your circuits class. In fact, some of you are in the circuits class, right? I would assume you have done the color codes already, right? Okay, and so you know that. For the rest of you, I think you're taking circuits next year or when you transfer. Okay? And so you put little color codes on here. So if I look at this one, it has a red, red, brown, and then kind of a silver. What does that mean? Right. And so you'll see in table 1, and like I said, I just really want to introduce you to the code. I don't expect you to memorize this. I would assume you guys in circuits have memorized this and you know what the ones are so you can figure it out in lab. But for the rest of you, I just want you to get ready for that this is what they're going to look like. The truth is, in our lab, you'll take something like this, and you can look at the color code if you want, but we'll just hook up the meter. Go, oh yeah, there's the resistance. And so we'll just measure its resistance. It would be more accurate than the color code anyways. Because as the last one is going to say, it's only a 10% accuracy here. But here's what it would mean. You would have usually, not always, sometimes there's only 3 colors, sometimes there's 4, sometimes there's even 5 colors. But this one has 4. And so you can see that, and not from your distance, but as I look at mine, it goes red, red, brown. So what does the red mean? It means the number 2. So if I wanted to know the resistance of that, the first red color would mean 2, right? What does the second red one mean? Well, it also means a 2. The third one is a little different though. The third one is what they call the multiplier. It's 10 to whatever number that was. See how the 2, 10 to the 2, 3, 10 to the 3? So mine was brown. So what does brown mean? Well, it means 1. So you multiply it by 10 to the 1. So this comes out to be 220 ohms. So that would be the resistance of this one. Now the very last band, the silver one, means that, hey, it's 220 plus or minus 10%. So it might be a little more than that, might be a little less than that. If I really wanted to know it, I'll hook it up to the meter. That's why I said for this class, we'll actually just hook it to the meter. When you hook it to the meter, maybe it'll come to be 223 or whatever. And so like I said, we won't do too much with the color code, but I wanted you to see it. I'll do another one here. This looks like a red, yellow, orange. Red, yellow, orange. All right, so what would red be? 2. What would yellow be? 4. What would orange be? Yeah, 10 to the 3. So this is 24,000 ohms. Right. And so that's how those color codes work and how the different bands work.
Why don't they just like stamp?
Because these were made a long time ago, and then stamping them was not really an option. So painting the colors on them was a better option. Yeah, yeah. Yeah, too easy, right? Yeah. Yeah, with today and our ability to do it, it's really the same question. I think one of you asked me last semester in Physics 121, I mean, how do I represent a vector on the board? If I said force was a vector, what do I do? Don't I put an F with a little arrowhead? But when it's in your book, how do they represent a vector? Right? So why do I do it different on the board in your book? And no, it's not just to confuse you. Again, it goes back to old printing. Making a little arrowhead on a print used to be very, very difficult. Or it used to be impossible, then difficult and expensive. Now I don't think it would really matter. I mean, you've got all kinds of nice little graphic laser printer stuff and wouldn't take much effort. But making a bold on the board is a pain. So we do this on the board to teach it, and then we do this when we're reading about it in print. Yeah. But I think if we had to do it all over, we would have the same set. And I think same thing for resistors. You'd probably just stamp it on there and say. And with all that said, you'll see the resistors we use in class, they're stamped on there. I don't think you're going to see any with the color code. Okay, but some of these resistors also, I guess as another point, they get really small. And even if you stamped it on there wouldn't be enough room to read it. You'd have to get a magnifying glass to read it, even if you stamped it that small. Some of these are really, really small. So, all right, well, one last thing, and we're done with the chapter. And maybe there'll be a time to do an example or two, or maybe that just have to wait till Tuesday here. But we probably should ask one more question. Maybe I'll put it here. As we begin now to hook up our circuit, let me draw something new. You've seen this symbol before. Let me just say it's 6 volts. Or maybe I'll even put a switch in here. No capacitor, but this little squiggly line, what's this? Yeah, so there's R. So for many of you this might be new, is what is the symbol we are going to use for these resistors. So this is what our circuit will look like. And so I guess we've learned the symbol for batteries, we've learned the symbol for switches, we've learned the symbols for capacitors, and now we are learning the symbol for resistors. So this would be a very simple circuit. Just a little battery, a switch, and a resistor. I would say then that if I were to ask how much current is flowing in this circuit, how would you get it? Yeah, there's the Ohm's law. That was the whole point of this long discussion. To figure out how much charge is actually flowing, I would take the voltage divided by the resistance, right? That would tell me. Now, what would happen if I increased the voltage? What would happen to the current? It would increase. On the other hand, what happens if I increase the resistance? It would decrease the current. As we get into our circuit, especially as we get started with the next chapter, we'll see if this helps. Here is my analogy to Ohm's law. If I were to turn on this pump, here we go. We might say something is flowing. Now in this case, it's water molecules that are flowing. Fair enough? And so the analogy is I have flowing water. Over there in the real circuit, I have flowing electrons, right? Moving charges, okay? But if I were to ask you what is giving it the energy, what is pushing the water, you would say it's what? It's this pump. And so this pump is purposely set on a power supply that I can change it. What do you think would happen if I turn the power supply down? Right? And that is hopefully going to help us as we begin to understand our circuits. That the voltage is one of two factors that determine how much flow here. Little voltage means little push, means little current, right? If I turn it up, I get a bigger push, bigger voltage, more current, right? But again, looking at that picture, what else affects the amount that flows? The resistance. So what do you think might happen? Even if I leave the power on really high, what happens if I pinch it a little bit? I got resistance. This is my resistance to flow. And so I still have some flowing. I can increase the resistance even more by pinching it harder, and I get less flow. I can reduce the resistance by pinching it less, more flow. And so our little circuit here hopefully will help us with the real circuit. So this is the pump, this is the push, this is the stop. The two together determine how much flows. Now let's think about this as it's flowing here, as we begin to study this in more detail, or more careful detail here. Now, the electrons are going this way, right? What direction is the current? Ah, good. So will it be okay if I just put a little I like that with a little arrowhead saying there's the current? Right? See, that's where we got started today. Is we're saying, what is the definition of current? The rate at which charge is flowing. And so if these are negative things that are moving, the current is opposite to the direction they're flowing, right? Okay, so we're going to say the current is flowing this way. So here comes the current. It's flowing. It's flowing. It's flowing. Now, you might say that that's really electrons flowing the other way. Okay, fair enough. But for the sake of conversation, let's just say it is 5 electrons every second, which obviously would be a very, very small amount of charge and a very, very small amount of current. But for the sake of discussion, it's 5 electrons that flow every second. If you watch them flow, if there's 5 every second before the resistor, how many is there after the resistor?
They get stuck at the switch.
Oh, well, yeah, I got to close the switch. Okay, fair enough. All right. So now there's 5 every second going into the resistor. How many? Same. Why the same? Okay, conservation of charge, right? Are we going to create any electrons? No. Are we going to lose any electrons? No. So keep that in mind. I told you earlier that this is going to be a very important principle. It's going to be more so when we get to the next chapter. But as we look at them flowing, here's what we're saying. It is really back to this circuit. If I came over to here and I said 17 water molecules go here, how many water molecules come out? 17. I didn't add any new ones. I didn't take any away. The fact is, when one moves in, it gets close to another one and pushes it out. And so the number of electrons that go through the circuit is the same. And I think sometimes that's hard for students, beginning students to see.
So if your wire was made of carbon, couldn't you actually create electrons by... You said that
No. Well, let me be real careful with that description. When you take carbon or any material, there's a bunch of electrons that are around the nucleus. And there is one of them that perhaps breaks free and moves from atom to atom to atom. Okay? And if it is copper versus carbon, copper, all of a sudden, every atom releases one, but not all of theirs. Carbon, on the other hand, only every, I don't know how many, I'll say every 5th atom releases it. When you heat it up, then every, say, 2 out of 5 release it, which is why it becomes a better conductor. But the same principle applies, that when one electron comes in, it forces another one, which forces another one, which forces another one out. So do you ever gain a number of electrons in here? No. Do you ever have more that come out? You couldn't, because what if you did? If you had more come out, wouldn't this thing start to build up a positive charge? And wouldn't that suck them back in? So that's kind of our argument. Maybe 1 or 2 more come out than go in. But you're not going to have 6 billion more come out than go in. The forces just get too strong. And so our argument always is, however many go into that resistor is going to be equal to however many come out of that resistor. The same thing here, how many go into that wire go out of the wire into the resistor, and out of the resistor into the other wire, and out of the other wire into the battery. And so that's the first thing I want to emphasize here in our very first simple circuit here, is that the current has got to be the same everywhere in that little loop. You don't lose electrons. You lose energy.
You're saying that we had 5 electrons per second, right?
So
once it goes through the resistor, are you thinking it's going to take more time?
Why would you say more time?
To resistance of flow.
Oh, okay, so
Well, I know there's going to be the same amount of charge on the other side, but the electrons are going to be traveling at the same velocity.
yeah, they are. They are. And again, I'll try to answer that in 2 ways, but can you see this analogy again? Isn't the speed of the water here the same as the speed there? Okay, now, if you say I'm going to pinch it here, okay, I would say it's the same amount of water. Now it's a smaller area, so then you might say it's going faster through this little pinched area. Okay, fair enough. But the total amount of water is the same. And that's what I'm interested in, not really how fast are they going, but how many of them are there.
Right, so if you remove the resistors, then it would be more electrons per second.
Yeah. So the amount of flowing depends on how much resistance. So if I put a smaller resistor, or as you said, just removed it altogether, which meant my resistance only comes from these wires, which is probably pretty small, then I'm going to get a lot more current. And instead of having 5 electrons a second, I'll have, say, 1,000 electrons per second. But it's still, if I have 1,000 per second, I have 1,000 per second everywhere. Did you catch that? And I want to make sure you saw that. That's going to be an important physics principle that's going to allow us to solve very complex circuits here. We're going to eventually call this Kirchhoff's node rule here and say however many electrons flow into an object equal the number that flow out. It's got to be that way, otherwise you would be violating conservation of charge. Okay? And so that's one of the big pictures I want you to see at first here. Now, let's look at the potential. Okay? And so if I was going to, say, draw a graph which measured the potential at different spots, and maybe I'll just put the letter A here, and the letter B here, and the letter C here, and the letter D there. And for the sake of giving a reference place or a place to start, let's say I start at point A. And so we'll look, okay, what is the voltage at A? What is the voltage at B? What is the voltage at C? What is the voltage at D? Okay? If I can imagine going from A to B, would there be a change in potential? Yeah, that's what we meant by this little symbol, right? This little symbol is saying, without really discussing the chemical reactions that take place in this battery, that is saying that there is an increase in voltage. It's because of the electric field that is created because of the chemical reactions that are in there. And so if I start and say, all right, this end of the battery, the lower potential, and we can call it anything we want, just like we did gravitational potential energy, we're going to do the same thing here with electric potential energy. I can start down here and say, look, there's some energy there, and then it increases. Now in my picture, I have it increasing to 6 volts. That's just given from the fact that I said this is the voltage on the battery. So I would say as I travel through the battery, the potential increases. If it helps, you can again think of this as gravitational potential energy. This part is the lifting of the water, if you will. If you think of this as a circuit maybe a little different, this one I had a pump, but if you think of this like a, you ever gone to one of those amusement parks that got the water slides and stuff, you know, raging waters? You know, this is the part where the pump is giving it energy. It is lifting the water up. Okay? Now it gets up to the top. Let's talk about B to C. In B to C, if the wire is thick and not very long, I would say it can move pretty easily from B to C, right? In other words, I'd say there's not much resistance. If I think about Ohm's law here, I could say, well, the change in voltage is how much current times the resistance. But again, if this wire is made out of copper, if this wire is not very long, if this wire is pretty fat, what would I say the resistance is? Approximately. Is 0. So what would be the change in voltage? What would be the change in energy? Yeah, it's 0. Now in reality it might be a small change, so maybe I'll put point C just a hair down and say, well, there is going to be a small drop in voltage. But again, according to Ohm's law here, Ohm's law is telling you how much the voltage dropped. And that's what I wanted you to see. There is a very little drop in voltage, very little decrease. Going back to this analogy, this would be again at the water park. I've just pumped the water up to the top. Now the water kind of flows in that level platform that everybody stands in to get onto the raft before they go down. It doesn't change any energy up here. The water kind of just easily moves back and forth, kind of seeking its own level. Okay, no change in energy yet. Now it's about to change, but it's still real high.
What type of problems do we neglect the resistance of the wire?
Okay, well, yeah, so it depends how big this resistance is to the wire.
Like if we were solving this, would we write B and C as equal? Like if this were a homework problem.
Depends if this resistance, chances are a wire has a resistance of, say, 1/100th of an ohm. So compare it to here. If this is 1 ohm or larger, ignore it. If it's 1 ohm or less, don't ignore it. Okay. Okay, now the big part of this. The big part of this is what happens from C to D. And I guess I better go kind of quickly here. We're out of time here. But C to D, yeah, there's going to be a lot of resistance. And why? It could be the material, it could be the length of the material, it could be the cross-sectional area. If this is a light bulb, usually it's the cross-sectional area. That tungsten filament is usually very thin. But the point is, there's usually a big drop. And almost all of it. Why do I say almost all of it? Yeah, the same logic from D back to A has to be pretty much the same level, maybe a slight change. But this drop then is probably pretty close to 6 because this increase is close to 6. Did you see I just used conservation of energy to justify the 6? Did you see those two principles? Conservation of charge is how I justified the current was the same. Conservation of energy is how I justified that the voltage around the loop is going to be 0. It's going to go up as much as it goes down. The water that goes up the amusement park goes up. How far does it fall down before it goes up again? The same distance. It doesn't fall half. It doesn't fall more. It falls the same distance down. All right. Well, real quick. I know you're ready to go. So here's the answer here. Let me put the change in energy then. The change in energy through my circuit is charge times change in voltage. You remember that equation? Yeah. Let's take one more step and divide it by time. What would you call change in energy per time? Power. Good. P for power. What would you call this? Current, charge per time, times voltage. So how do you calculate the power in the circuit? I times V. If you also put this with Ohm's law and replace V with IR, you get I squared R, or you get V squared over R. You've got three formulas you can use to calculate the power. So the battery is delivering power to the circuit. The light bulb is taking power out. How does the energy delivered by the battery compare to the power coming out? Equal. Why? Conservation of energy. Exactly. All right, that's the last formula, and then we'll do some examples on Tuesday.